Welcome back. In the last video, LSTMs solved the vanishing gradient problem and gave our models a real memory highway. So, for years, sequence to sequence tasks like translating French to English or generating captions for images relied on pairing an RNN encoder with an RNN decoder. But as sentences and sequences grew longer, researchers slammed into a massive architectural brick wall, the bottleneck problem. So today, we're looking at why compressing sequences into a single vector fails, and why the revolutionary mathematical fix that changed AI forever, the attention mechanism. To understand why early translation and captioning models struggled, let's look at how they were wired. You'd have an encoder network read the input sentence one word at a time. At the very end of the sentence, the encoder would take everything you just read and compress it into a single fixed-size array of numbers called the context vector. Then it would hang that one little vector to a decoder network to generate the translation. So imagine like reading an entire novel and then being forced to summarize every plot point, name, nuance into a single 3x5 flashcard before handing it to someone else to rewrite the entire book. It's impossible, right? That single context vector is an informational bottleneck. For short sentences, it's fine, but as sequences get longer, the network is mathematically forced to forget the early details and just make room for the end. In 2014, researchers asked a brilliant question. Why are we forcing the network to memorize the entire input sentence before it starts translating? Why not let the decoder look back at the original sentence whenever it wants? This is the attention mechanism. Instead of relying on one static context vector from end of the encoder, attention calculates a brand new dynamic context vector for every single step of the output. So when the decoder is about to generate a word, it scans all the hidden states across the entire input sequence, deciding which specific words are most relevant to the word it's building right now. You can actually visualize this happening. In image captioning, where a convolutional neural network feeds visual features into a RNN decoder, we can map the attention weights as heat maps over the original photo. When the AI generates the word cat, the attention spotlight illuminates the whole animal. But the second it generates on the word paw, the spotlight instantly zooms in on just the paw pixels. Similarly, in like language translation, attention learns grammatical structure automatically. It knows that to translate a French adjective, it needs to attend to a word that appeared earlier in the English sentence. It no longer forgets long sequences because it never has to memorize them. It just has to look at the source. Here's an example with the word paw and the cat. So, how does the math actually work under the hood? So, it happens in three steps. First, we calculate alignment scores. We take the decoder's current state and compare it to every single encoder hidden state, usually using a simple dot product to measure how relevant each input word is to our current step. Second, we take those raw similarity scores and run them through our old Softmax. If previous videos mentioned Softmax. This turns the scores into a clean probability distribution where all weights add up to 100%. Maybe word 1 gets 80% of the focus, word 2 gets 15%, and word 3 gets 5%. Third, we multiply each input vector by its new softmax weight and add them together, creating a weighted sum. Words with high attention weights shine through loudly, while irrelevant words get multiplied by near zero and fade into the background. That final weighted sum becomes our dynamic context vector for that exact moment. And here's a graph with some explanations about each step. So attention completely fixed the bottleneck problem and shattered performance records across deep learning. But pretty soon, researchers noticed something curious. If attention is so incredible at gathering context across time, why are we still using slow sequential RNNs to process the data in the first place? So in the next video, we're looking at the 2017 paradigm shift that threw away recurrent networks completely and birthed the modern Gen AI revolution, the transformer.